Objective 8.7, Graphing Logarithmic Functions. So we've already talked in our last objective about what it means to be logarithmic and how it relates to the exponential form, but we talked about it in terms of the algebra. Now, just as a quick reminder, remember if we have y equals log base b of x, that is the same as having b to the y power equal x. And we said in the last objective that that made these two functions inverse functions. So we saw what that meant algebraically in the last objective by talking about if we switch the x and the y here, then that would end up giving us an exponential function. But what does that mean graphically? Okay, so here are two graphs. One is in green, the other is in blue. The red dotted line here in between them is the line y equals x. And if you remember from when we talked about inverse functions last year, we said that graphically inverse functions have to be reflections of each other through the line y equals x. So if my green graph represents an exponential function, which hopefully you recognize it does, then the reflection of that would be the blue graph, and the blue graph then would be a logarithmic function. Now notice how they compare here. First of all, if you remember, in the exponential function, without any a, h, or k values, we always had a key point of 0, 1. Because if I had a function like 2 to the x power or 5 to the x power, when I put 0 in for x, I would always get 1. So if that's a key point on the exponential function, then what's going to be a key point on the logarithmic function? Well, hopefully you remember that we can switch the x and y coordinates for all points on one graph to get the points on the inverse graph. And so if we have a key point of 0, 1 on the exponential function, then that means we're going to have a key point of 1, 0 on the logarithmic function. We also need to take a look at the way the graph curves. With an exponential function, we know that it curves so that it bends down and gets closer and closer to the 0, to the x-axis, as our x values are getting more and more negative. Okay, well, when we reflect that through the y equals x line, now our curve is getting closer and closer to the 0 of y, which is the y-axis. Excuse me, the 0 of x, which is the y-axis. So now we're coming in closer and closer here, instead of up here like we were on the exponential function. So if you can take what you already know about exponential functions and just in your head kind of flip it over, that's going to give you an idea of what your logarithmic function should look like. It has a key point at 1, 0, and it's going to curve in so that now our y-axis becomes a vertical asymptote instead of our x-axis, which was the horizontal asymptote. All right, so let's make some comparisons here. Let's take what we already know about exponential functions and see how those things turn out for logarithmic functions. So I've listed 3 different exponential functions here as possible examples. We have 5 to the x, we have 10 to the x, and we have e to the x. And then I've listed the corresponding inverse function as logarithmic functions. So if I have a base of 5 here, then I have log base 5 of x here as the inverse. 10 to the x here means the inverse will be common log 10 of x, log base 10 of x. And an e base here means that the inverse is going to be natural log of x. Okay? Now, what do we know about exponential functions? Well, let's start with domain and range. We know from our work a few objectives ago that the domain for exponential functions is always all real numbers, and the range is always positive real numbers, or y being greater than 0. Now, what do you think is going to happen for domain and range for logarithmic functions? Well, again, hopefully you remember that with inverses, all x's and y's switch. So if I have a domain, which is x values of all real numbers, that's going to become my range. And if I had a range of all positive numbers, that's y's, and so that's going to become my domain. So now my domain is that I have to have all positive real numbers, which is the same as saying x has to be greater than 0. And it's my range that's going to be all real numbers. Okay? Now, how about increasing, decreasing? With the exponential function, the type that we used in our example just a slide ago, we had an f of x that was increasing as x increases. Okay, so it was starting here and it was going up as the x got bigger. Well, what's happening with the logarithmic function? Well, you should be able to see that that also is an increasing function. It increases differently. It increases more slowly as x gets bigger, but it does still increase. So the inverse function is not changing the fact that these are both increasing functions. How about the limit? Where's the asymptote? Well, we talked about the fact that in the exponential function, the f of x is approaching the x-axis as x gets smaller. So in our graph, remember we have a curve that looks something like this. It's down here where f of x is approaching the x-axis as x gets smaller and smaller. Well, when we flip that over to our inverse logarithmic function, now the g of x approaches the y-axis as x approaches 0. So now we get that curve going the other way, and so now it's the y-axis that's going to be the asymptote, and our graph is going to be getting closer and closer to that y-axis as x gets closer and closer to 0. But again, from our domain, x is never going to actually equal 0 because it has to be positive. So if I have a function like 10 to the x, I know when I put -1 in for x, I'll get 1/10. When I put 0 in for x, I'll get 1. And when I put 1 in for x, I'll get 10. If I take the inverse function of that and take the log of x, then each of these ordered pairs simply gets flipped around to give me ordered pairs for my log function. And so we can use this idea when we're asked to graph. If we want to rewrite the log function as an exponential function, figure out some ordered pairs from the exponential, and then flip those ordered pairs around, we'll have ordered pairs for the log. Doesn't seem like the most efficient way to do it, but because we're fairly familiar with the exponential function, it might actually be the easiest way to go about it. So let's take a look at a couple of examples where we're asked to graph. Here we're given the function g of x equals 2 natural log x. We're supposed to graph using transformations and then state the domain and range. Okay, so here is sort of the process I would recommend. We know y equals 2 ln x is what we're supposed to graph. I would start by asking yourself, what is the parent function? What's the most basic logarithmic function that's in this equation? And in this case, that's y equals ln x. Okay, natural log of x. And if I want to, I can rewrite that into its exponential form, which will be x equals e to the y. Notice I have not switched the x and y here. I want to keep x and y where they are so that I'm getting the right points. I've just switched the form to change it from logarithmic form to exponential form. Okay, so now key point, well, as we talked about before, in this kind of parent function, the key point is going to be at 1, 0, so we can plot that. And then another easy point to figure out goes along with the base. If I know I have a base of e, then I know I have to have a point at e, comma, 1. Because if I put 1 up here in for y, then I know e to the first power is going to give me e as an answer for x. But when I put that into the ordered pair, the e for x goes here and the 1 for y goes there. Okay, so this is another ordered pair that I know has to be on my curve. And because we know e is approximately 2.7, I can go ahead and graph that. 2.7, 1. And I can keep going with that if I want to get some other points. For example, I could put 2 in for y. If I do that, I'm going to take e and square it, and that's going to get me about a 7.28. So now x is 7.28 and my y is 2. So there's another possible point. And so I can put in as many points as I think I need in order to be able to fit a curve. But eventually I do fit a curve that's going to go through these points and is going to hug in closer and closer to this y-axis. Now this is the curve for our parent function. Now I need to take a look at my actual function and decide what kind of transformation I need to do. Well, in this case, the other number that we're being given here is this 2, which is an a value. And so the a value is going to have the effect of making a vertical stretch of this graph by a factor of 2. So what that means is every point that I have on this curve, the y value of those points is going to be multiplied by 2 to get the points of my actual curve. And so my points are going to look like this. This point had a y value of 0. 0 times 2 is still 0, so it's going to be the same. This point had a y value of 1. When I multiply it by 2, I'm going to move it up here to y equals 2. And for this point, I had a y value of 2. So when I multiply it by 2, I'm going to get a y value of 4. And so now if I fit my curve to that and get rid of my parent curve, this is what the curve of y equals 2 ln x should look like. Now, in terms of domain and range, because it's our domain that is now restricted, it's only h values that are going to change what the domain is. Since I don't have any h value here, my domain and range will stay the general values that we talked about before. Domain will be x greater than 0, and range will be all real numbers. Okay, let's try another one. This case, we're being given the function g of x equals log of x minus 4. So let's go through the same process. The parent function, the basic logarithmic function, is just y equals log of x, which we can rewrite in exponential function as x equals 10 to the y. Again, we know the key point in this is going to be 1, 0. And this time, because we have a base of 10, we know that another point is going to be the point 10, 1. Because again, putting 1 in for the y is going to end up giving me an answer of 10, but my answer is actually x. So 10, 1 is another point on my curve. So when I try to fit in a curve to that, again, it's going to have to go through the point and curve in so that it's getting closer and closer to my y-axis. This blue curve is what the curve for my parent function should be. But now I need to do my transformation. So what transformation should I do in this case? Well, this time I have this minus 4 out here. And that 4 is going to be an h. So an h of 4 tells me that I have to move my graph 4 units to the right. So every point that I have on this curve gets moved 4 units to the right, and I draw a new curve. So I get rid of the parent curve, and this is what I'm left with. Now this time, when I'm looking for domain and range, I have to realize that I do have an h value here. So not only did every point get moved 4 units to the right, but so did the asymptote. And so now my domain is going to be that x is greater than 4 rather than greater than 0, because it also got moved 4 units to the right. So x is greater than 4 for domain, and range is still all real numbers. Why don't you give this one a try? You're being asked to graph the function log base 2 of x plus 3 minus 4. Try to go through the same process that we've just been talking about with the other two examples. And then once you think you've got a good approximation, go ahead and come back and we'll check through it together. All right, so if we go through the same process, our first step is to identify the parent function, which in this case will be log base 2 of x being equal to y. If we rewrite that in exponential form, then we're going to get x equals 2 to the y power. The key point to that is still the point 1, 0, so we can plot that. And then the base in this case is 2, so we know another point would be the point 2, 1. We could also keep going with points in this case and maybe put in a 2 for y to get a 4 for x and plot a point like 4, 2. Okay? After you've put in a few points to help you with your curve, you can fit the curve in, and that gives you the curve for the parent function. So now we need to figure out how to transform that. And in this case, we are given the plus 3, which means we actually have an h of negative 3. And we have this minus 4, which means we have a k of negative 4. So in terms of transformations, that means I'm going to take this graph and move it 3 units to the left because of the negative 3 for h, and 4 units down because of the negative 4 for k. So if I take every one of these points and move them 3 left and 4 down, they're going to end up like this, which means I'm going to end up with a curve like this. And again, remember that because I do have an h value, not only did every point get moved 3 to the left, but so did my asymptote line. So because of that, I now know that the domain for this should be x greater than -3, and the range should be all real numbers. Okay, well hopefully that gives you enough practice at graphing a few of these logarithmic functions so that you can do it on the practice. So next class you should be working on the 8.7 practice problems. If you have any questions about what we did in this video, please make sure you ask during class time. And then when you're finished with your objective, make sure you show Mrs. Gordon so you can get it checked off. And we'll see you next class.